This course module covers the basic technical principles of these vortex flow meters. After completing this module, you will be able to recognize the need for flow measurement in the process industry, recall the measurement principles of vortex flow meters, list reasons for the use of vortex flow meters, analyze the different application requirements and identify possible measurement principles. In order to make processes stable to ensure that the product quality remains consistently high, 3 physical variables usually have to be monitored and controlled: process temperature, process pressure, flow in volume units, flow in mass units. These 3 variables have to be measured not only to obtain process stability, but also for safety reasons, to make sure that asset specifications are adhered to and pressure and temperature limits are observed. Flow also often plays a major role in cooling or heating circuits or burner control. Flow meters are also frequently used for batching or charging and accounting purposes. Vortex flow meters measure velocity. The internal area of the meters is usually known. This means that volumetric flow can be accurately derived from the velocity measurement. Flow rates in actual volumetric units at the operating pressure and temperature are measured. Mass flow rates, or volumetric rates based on standard conditions, must be computed from the actual volumetric flow. In order to measure the flow velocity at one point in the line only, and to derive an average flow velocity from that one measurement, a certain flow profile with almost uniform velocity is necessary. To achieve this flow profile, 2 conditions must be fulfilled. A minimum Reynolds number is necessary, and the flow profile must not be disturbed by installations which may cause a non-uniform flow velocity in the pipe. The Reynolds number is used to determine the type of flow that exists in the pipe based on the process and fluid data. The image contains the general formula for calculating the Reynolds number. This is a dimensionless number, meaning that all engineering units of the individual variables, density, viscosity, velocity, and pipe diameter, are cancelled out when multiplied together in the formula. A low fluid velocity at a constant viscosity, density, and pipe diameter results in a low Reynolds number and a laminar flow, parabolic velocity profile shown at the top left, whenever the calculated Reynolds number is smaller than 2100. Vortex flow meters cannot be used for laminar flow. Wedge meters, positive displacement, electromagnetic and Coriolis mass flow meters are examples of devices that can be used to measure laminar flow. Turbulent flow, the almost flat velocity profile shown at the bottom left, exists whenever the calculated Reynolds number is greater than 3000. Vortex flow meters can be used in this turbulent flow. Transition flow, not shown in the image, exists with Reynolds numbers between 2100 and 3000. Vortex flow meters cannot be used to measure transition flow. The Reynolds number is important because it helps you to select the type of meter that can be used for a specific application. To create a Karman vortex street, an obstacle is provided in the flow to shed vortices at the edges of this obstruction. The obstruction in a vortex flow meter is called the bluff body. Over the years, an ideal shape has been found for creating reliable vortices over a long period without any wear at the edges, a trapezoidal bluff body. Many vortex flow meters suppliers install a separate sensor unit behind this bluff body to detect the frequency of the vortices, whereas other suppliers install the sensor element directly in the bluff body. The delivered frequency depends on the ratio of the pipe diameter, d, and the bluff body width, small d, at a constant volume flow. In addition to the shape of the bluff body, the piezo sensor also plays an important role in the vortex primary signal. Vibrations, hydraulic noise, and pulsation are always present in the pipe and have to be overcome, The flow signal detected by the sensor is therefore not an ideal sinus curve as in the theory. Intelligent sensing algorithms in the Vortex electronics have to distinguish between the two elements, the noise and the real flow signal. To achieve this, ABB implemented two compensation piezo elements in the sensor, in addition to the two flow piezo elements. The compensation piezo elements measure only the pipe vibration, whereas the flow piezo elements measure the flow signal plus the vibrations. The isolated flow signal is the signal from the flow piezo elements minus the signal from the compensation piezo elements. This makes the system ideally balanced and enables the transmitter to compensate effects from pipe vibrations. Furthermore, the PT100 is provided for temperature measurement for compensation purposes. Principle of operation. The frequency, F, of vortex shedding is proportional to the flow velocity, V, and inversely proportional to the shedder body width, D. Every vortex hitting the sensor carries a defined fluid volume. St, the dimensionless Struhal number, defines the quality of the vortex flow measurement. With the appropriate bluff body design, St is constant over a wide Reynolds number range, meaning that the volume per vortex remains the same. To find out what volume is transported per vortex, each flow meter is calibrated to evaluate the meter K factor, which is frequency over flow. During operation, the flow meter calculates the actual volume flow from the measured frequency and the meter K factor. In other words, every pulse from the sensor represents a certain volume V, regardless of the substance of the volume. This is why the calibration procedure is widely independent of the subsequent application. The density of the substance of the volume has an impact on the intensity of the pulse, but no impact on the pulse frequency. The higher the medium density, the stronger the signal from the sensor. This is why the measuring dynamics in gas and steam measurement change with the actual density of the medium, which is a function of standard density, pressure, and temperature. The K factor provides the volume information for one pulse hitting the sensor. This is self-explanatory. The flow direction is from the left to the right. The vortices hit the sensor installed directly. The sensor is installed separately behind the bluff body. The measuring principle works for all gases, steam, and liquids with low to medium viscosities. The independence from conductivity make these meters ideally suitable for all applications of petrochemical raw products, solvents, or boiler feed water. The measurement is independent of the density, temperature, viscosity, and pressure, as long as these are in accordance with the limits of the measuring principle and physical meter specifications. The design featuring a sensor unit, which is completely separated from the bluff body, makes the meter widely insensitive to deposits, pollution, or coating. Now that you've learned how this measuring principle works, you can understand why flow meters of this type cannot start working from zero, in contrast to electromagnetic or Coriolis mass flow meters, for example. A specific flow velocity is required to build up the Kármán vortex street and to reach the linear range. As a result, a low flow cutoff must always be taken into account. The bluff body constantly causes a pressure loss, which, in the worst case, may cause a cavitation in the pipeline. This cavitation is highly destructive and must be avoided by providing sufficient static overpressure in the pipeline. Although ABB's design is not sensitive to deposits, they may nevertheless cause measuring errors or failure. Therefore, typically clean fluids which do not tend to build up deposits are preferred. Two-phase media such as paper or sludge and wet steam cannot be measured. Liquids and gases are measured at completely different flow velocities, and thus a gas or liquid mixture will be measured under incorrect conditions. Minimum pressure. The signal quality is a function of the medium density and flow velocity. The higher the density, the better the signal received, and the better the signal-to-noise ratio. The requirement of 0.5 kilograms per cubic meter is given in order to meet the full meter range. In hydrogen applications, for example, a minimum pressure of 5 bar gauge or 72.5 psi G, respectively, is required to meet this limit. Vortex flow meters always measure the actual volume flow of liquids, gases, or steam as the primary signal. This means that one pulse at the sensor always refers to the same specific volume. However, the content of the molecules inside this volume is influenced by temperature and pressure. This influence has to be compensated in some way. Every volume contains a number of molecules which require a certain space. Temperature and pressure do not influence the mass, but do influence the volume, because the number of molecules does not change. In liquid measurement, the impact of pressure is typically ignored, because ideal liquids are not compressible, whereas gases are. Temperature has an impact on both liquids and gases. The volume typically increases with increasing temperature. In order to compensate these influences, vortex flow meters offer different operating modes. For liquids, with and without density or volume correction. For gases, with temperature compensation only, or with temperature and pressure compensation for standard or mass calculation. For steam, depending on the type of steam, with temperature compensation only for saturated steam, or with temperature and pressure compensation for overheated steam. Modern vortex meters with enhanced computing capability can calculate the energy flow directly from all of this information. Now let's summarize this learning module. What have you learned so far? You can recall the measuring principles of vortex flow meters. You know the key elements of vortex meters: bluff body, piezo sensor and transmitter with intelligent sensing algorithm. You can recognize application features and limits when selecting and sizing vortex flow meters.